So welcome back everybody. I'm so glad everybody has now a mission idea. And there was a bit faint points in some mission justifications, but everything is going to be really nice and you're going to be excellent missions. Now we're going to talk very shortly about system engineering. So this is actually the next part. What are you going to do with your mission? It's called system engineering. So let's see, does this work? No, this doesn't. This works. So this is your chart, and you are pretty much here. Maybe some most advanced ones have already also the mission name, which would be nice. But mission objective and mission requirements is actually one of really big hard works. And now you have to find your payload, which actually brings you there. You have to define an orbit, a spacecraft configuration. That means, do you need one spacecraft, or maybe you need two, maybe you need 10. For example, there was an idea of measuring polar auroras at the same time from both poles. Then you need two spacecraft. And then you also need something to think about ground segment, what kind of ground segment you will have. And this will give you actually the entire mission description, more or less, what you have there. And then to design a bit also the spacecraft. What kind of subsystems do you need? So I expect a product tree, what kind of subsystems there are. And also the most important, budgets, and maybe something about risk, cost, and schedule. Okay, let's go to system engineering. So system engineering is a logical process of activities that transforms a set of requirements arising from a specific mission objective into full description of a system which fulfills the objective in an optimal way. So that means, like, already in definition of system engineering, you start with requirements, which is giving you the full description, and it describes a system which fulfills the requirements and give you a result you are after, filling the objective. So system engineering is a sort of engineering, sort of bureaucracy, but why are we doing system engineering? So this is a study which is analyzing how errors penetrate throughout the different kind of engineering projects and missions. So the error cost escalation through the project life cycle. It's actually done in NASA. So in the requirement phase, you make an error and it costs something. If the same mistake is done or revealed in design phase, it's already 8 times more expensive. If you find this problem in build version, you will spend 16 times more money. And in operation wise, it's 29 times more money you spend to mitigate the problem. And if there is software involved, it's even more crazy, or how it is. So, from last lecture there was already shown this slide. First you have to specify why you do something, and then what to do. To specify requirements. What kind of things you have to measure, what kind of instruments you have to have in order to carry out the mission. And the engineering part, or system engineering, is very much coming here, how. But also these first parts are part of your system engineering. Otherwise you cannot proceed. So requirements we went through. The requirements are organized usually in different levels, and you have top level system requirements, which are actually coming very straightforward from your mission objectives. For example, this is a Mercury mission, and they have a top level system requirement that the spacecraft design shall guarantee the operational lifetime in the environment dictated by the orbit parameters established in chapter So this is a top-level requirement that if you go to this place, you have to survive there, and you have to survive as long the mission is defined. And these are coming from different other requirements already. It is important to actually make traceability in your requirement. So every requirement which is not top-level requirement should have a parent requirement. If you start to write the software, you really find it useful that you actually see where this requirement is actually coming from, why we need to have some of the very stupid requirements. And then it might be that you really can't do without this requirement. A product tree, a very typical system engineering approach. So what you have is just a block diagram. Block diagram, what you need to have, how they are connected with each other, and what they are doing, what kind of interfaces they have. So there is different ways to do this kind of product trees and block diagrams. So this is another student work. There is a space segment block diagram. Actually, try to keep in mind that in space mission, there is not only space segment, there is also ground segment and space segment, and they both are important. So somebody has to also make design for ground segment and also establish the interface between ground segment and space segment. But essentially what you have here is the subsystems of a typical spacecraft. You have structure, thermal systems, propulsion and orbit and attitude control, avionics, power, communications, and then payload. So this is very much typical for most of the spacecrafts. Of course, some spacecrafts can even have like passive payload, but in most cases you have something like this. Then a really important tool for all system engineers are budgets. So what you start to work is, you know already in the beginning that, okay, I have limitations. I have limitations that our satellite cannot be bigger than 1.3 kilograms. It just can't. And in order to then share the whole mass between different subsystems and everything, you need to make tables. And these tables are called budgets, like also if you're managing a company or if you're managing a country, what you need to have, you have to manage your resources with budgets. So this is the most reasonable way to do it. There is 3 key budgets for your spacecraft. Mass budget. This is often very restricted, you cannot go over it. You have power budget. Sometimes you can build bigger solar panels and you can actually increase your power budget. And then you have telemetry budget. This is also one of the very limited factor. If you, for example, have a mission to Mars, then you have to think how much data I am able to transfer and how to share this data amount between different important payloads, because all the payloads, all the subsystems, everybody would like to have a lot of data, but you have to somehow identify what is actually important. Your budget should be, in a space project, always up to date and available for all your engineers in the project. And it's most important also to have margins. So if you start a space project or whatever kind of system engineering project and you make up your first tables, use margins, contingency. That means that you know that my payload is going to be 400 grams, but you put to the table 460 grams. Because you know that these guys are going to forget something, they need bigger screws or whatever, and the mass can grow. So you have this budget sort of buffer in the entire satellite. And all the space projects have been proving that you're most probably using up all your margins by the end of the day anyhow. So start with the safe margins, and these margins are even documented and decided by ESA. If you work in the ESA project, depending on the tier level, how is your technical readiness, or how close you have, how close is your subsystem for a real flight model, then how big margin you should have in your tables. Interfaces. Engineering is all about interfaces. So interfaces are between your satellite and the launch port or deployment port, between of all the electronical devices, all the mechanical devices. You have electronical interfaces, digital interfaces, thermal interfaces, a lot of interfaces you can have. What you should do in the beginning when you start to build a project or build a system, make some kind of sketch of your interfaces. How these different ports are connected to each other. Do they have a bus connector? Do they have cables? Maybe I use optical link inside the satellite, a radio link, whatever, everything is possible. But you should start to document your interfaces. And especially in the bigger projects where you have subcontractors. Subcontractor does not see anything else from your project, maybe, just the interfaces. And if the interfaces are not right, are not made in a purposeful way, so you can end up with a totally wrong system. So they are just not fitting together. So you have to work with interfaces already in the beginning. So these are all some sort of interface drawing. So you start with the sketches, how these things are fit together, what kind of systems you have, what kind of interfaces you have here. Work interface, I2C interface here, power lines here. So you start to draw where your interfaces are going. Most probably, again, you have to do during this process, you have to do a lot of trade-offs. And your requirements is the compass you are using in this process. So if you need to make a decision, you make a trade-off and you see, according to your requirements, how to fill the requirements, how to build the system. Testing and developing. So, especially in CubeSat project, I think it's very useful to start testing as fast as possible. Even if you have the first breadboards or even first components. So even if you order the components, normally what you're using is commercial off-the-shelf components, normal components for ordinary electronics, and there is not necessarily space flight heritage for these components. So it would be a good idea to thermocycle, bake out, and do a couple of vacuum tests for these components and see do they withstand this environment. Already in the beginning, it's just prototyping. And during this prototyping, then you actually can start to fiddle with the software. You get to know with the interfaces of this component. You also make the rigs, make the breadboards, how you can test it, and so on. Maybe even you can write part of the software, which might be used even in the satellite itself. But this testing in early phase is I think, one of the keys to success in a CubeSat project, at least. And build a lot of prototypes. So CubeSat mission is totally different mission than, especially educational CubeSat mission, than the real big space mission, where all the engineers, they have experience. They have been doing this for a long time, and they have experience. So what is experience? Experience is sort of accumulated mistakes. So you have been making a lot of mistakes, and then you are getting experience. And so it's better to make these mistakes in early phase. Start to make your mistakes as fast as possible. So make mistakes, make prototypes, test those prototypes as fast as possible. And students most probably don't have this kind of experience, so they have no, they cannot imagine the system they have never built or never seen. And really educated, maybe experienced, 10 years of experience space engineer, he can see, like say, yes, we should do like this and this like this. But the student cannot know about these things. So only possibility to really grow fast on this experience side is make prototypes. Software, this is the biggest troublemaker, even for commercial satellites, but especially for CubeSats. So approximately half of the CubeSats a couple of years ago were still failing or suffering because of the software. And if you start to write the software, you're actually coming back to the very beginning requirements. Software engineer is coming to your project and saying, okay, I can write C, I can write Ada, I can write anything. So where are the requirements? What the software should do? So if you have requirements, you can work from the requirements to the pseudocode and define what the satellite should do, what kind of measurement should be, and then you come back to the solution what software should do. If you don't have requirements, your software engineers are fiddling around and they are really lost because they don't know what the software should do. And if you have software engineers, most probably it's much too much to ask that he would also understand all the science behind it, all the small things there. Another big problem and troublemakers is connector and cables. So if you start to assemble your system, you have mostly been developing breadboards on your table, and there's no problem. You always have some cables going around and everything is nice. And then you start to pack this thing into a very small 1 liter jar, and it doesn't fit because your cables are all on the way. So couples of good hints. If you start to draw your cats, try to draw already cables on this cat. If you are not drawing cats, at least draw the connectors with counterparts. So I have seen a lot of designs where it's nicely connectors on the edge of the board, and then you ask like, okay, but I have a speed counterpart for this connector. Where it should go? I don't know. So it's really good practice to draw all the connectors with counterparts on your board. So you start to see where the cables are going, what kind of things are happening inside the satellite. Keep in mind also that all the cables, practically, have bending radius, especially RF cables or optical cables. So it is not just like I'm putting the connector here and connecting the cable. No. Sometimes you should leave like 3 centimeters for the cable. And if you have only 10 centimeters here around, so it might be a serious issue. And make, in early stage, mock-ups, prototypes, and make integration tests. All these problems are popping up in early stage if you're starting to do integration tests in early phase. Documentation. Already was talking about documentation. So you should try, at least in a CubeSat project, develop a documentation approach. Might be paper-based, might be just a big sheet of paper on a big wall, or something, but you need to have a place where you get your right numbers down. And as fast as you start to fiddle with documentation, you realize that I need to have some kind of version control. So who has been writing in my document? What is this 3 here? Is it like real number or not? So if you have a version control, you can check. And maybe even if you have a proper version control, nobody else than your system engineer is actually not able to change this number. So you know that this is coming from a system engineer and this is for real. And as I said, documentation doesn't need to be on the paper. So this is one of the, unfortunately colors are not so nice here, but one of the charts which is explaining how the information should know. So you have a system level and then you have subsystem. Here is your system engineer who is giving, for example, this subsystem can have 200 grams, this can have 175 grams, and so on. And there is a subsystem engineer who is making the subsystem, for example, the radio, and he knows I have 125 grams. So the subsystem should see all the time the actual values which are valid for the whole system. At the same time, he can communicate and send his current values. Most probably, if you start with a prototype and start to make a prototype system for a radio, for example, the first prototypes are much heavier than your actual design going to be. But you can mark down your values here. So the system engineer sees your values, and it should be arranged that system engineer can only change these values here, and your subsystem level engineer sees those values and can change his own values. And also system engineer can see his values. That means he can see like, okay, this radio thing is not congregate. They should have 125 grams, but they're constantly like 150 and plus. So we should do something. So system engineer can take in early stage measures and say like, okay, let's cut this from somewhere else and give these guys 30 grams and we can get the system going, because it seems like this is not possible to actually squeeze down. Procurement. So if you start to buy things, even off-the-shelf components, off-the-shelf subsystems, everything takes time. Everything actually takes much more time than you believed. And then the thing starts to roll in. You should have a storage system and handling system, and you should document your orders somehow to know what is going on, even just like filing the papers or something. And in very many projects are delayed because procurement takes time, and you cannot even foresee everything. That's why also making the schedules should be made with margins. So you put some extra time everywhere. In early stage, this is coming from big space projects, the model philosophy. But model philosophy is actually good to decide already in a CubeSat project also in the beginning. So what kind of models are we going to build? So you think, okay, we are building one satellite. In most cases, even for big satellites, you're building at least 3, 4, 5, sometimes 6 satellites, almost full size, before you launch one. So you have flight model, you have flight sphere model, you might have qualification model, which is actually shaken to death. There is engineering model, which is almost similar to the flight model, and so on. So you should take a look what does model philosophy mean, and how many models you can afford to build. If there is one very expensive part in your satellite, there might be like, for example, you have to go with a protoflight model. You have just one part and you try to develop this to the fully flight model. Or if you have cheaper parts, it's actually good to build more models. The more models you build, the bigger is probability that your equipment is going to work on orbit. So this is one of the almost engineering models of R1 satellite. Make schedules. Although these schedules are most probably nothing close to reality, but they at least give you a sense how you should take things into account. So just very sketchy block diagrams, what happens when and what happens next would be really good, and would be really good to have this available for all the team. But scheduling in a student project is the most probably the biggest challenge. This is almost impossible. Make reviews. So reviews is really important. So most student projects at least are sort of deadline driven. If you have deadline, things happen. If you don't have deadlines, things are not happening. So review is really handy deadline. It has a real meaning. You have to get things ready, and if it's done, you get feedback from independent experts. So yes, these are the reviews which are typical for bigger space project, but you can make small reviews. Even, for example, let's have one design for metal parts, or the structure parts are ready, so let's order those. Wait a moment, let's have a small readiness review, like just maybe manufacturing readiness review. And a couple of guys are going through with a mechanical guy. Is it ready? Yes. Actually, it looks like you have been forgetting this hole for this antenna cable here. Please make it also, and then it's ready. So it really helps also to keep the schedule. Risk analysis is part of the space project, but maybe here in CubeSat project, this is the area where you most probably are not going. And also ECSS standards, it's really handy to read if you don't know how to glue something or what kind of transistors you should use. But this is really heavy stuff, and people will get really fast scared of if they start to read these documents. So this is all about system engineering, and coming back to this, any questions? So now let's make these wonderful missions happen. Try to make a poster which somehow covers these areas. You have computers, you have CubeSat, you have your ideas. Hammer, make a mission. You should have an objective, you should have some kind of requirements and some kind of payload. And then try to sketch what kind of system you should have. Does it have attitude control? Maybe it has a propulsion. Most probably it needs communication. What kind of communication antennas we have around? Do we need fast communication or slow communication? Budget. Really easy to make, for example, a mass budget because it's standard. 1 cube. If you go with a 1 cube, 1.3 kilograms, pretty free actually. So telemetry budget, a bit more tricky, but you can get a radio defined from a commercial provider, and it actually states how much information you can transmit. And then you should fit into this transmission all what you have to transmit. For example, if you have very slow link and want to have a spectral imager, not going to be possible because your link is too slow. And if you have some idea about cost, would be also nice, and scaling. Are you going for a 2-year project really fast, or are you going to do like 30 years technology development project when CubeSat might be not around anymore? And Mark, what is the time when these posters should be ready? It should be like 20 minutes before so 4:30, isn't it? No. Yes. Let's try to have 4:30, and then we make a very fast review of all those missions, and we're going to have missions in this way. All these mission posters will be attached to the wall. All the people will be divided into 4 groups, and all the 4 groups will have presentations at the same time, 4 times. First, with 4 posters, we switch places, and we switch presenter again, the same presentation with the same posters. So all the people will see all the posters, but with a different presentations. And jury is part of this audience team and give you some numbers. So we're going to have a competition who has the coolest mission. Any questions? For a poster, I think what we have is pen and paper. So it will be just fine. Use pen and paper and make your poster there.